Hello and welcome back to the course on deep natural language processing. Today we're looking at the bag of words model. First thing I'd like us to look at is an email I received just a few days ago. So here we go. The email is about a catch-up, and my friend is asking, hello Kirill, checking if you're back in Oz. Oz stands for Australia. Let me know if you're around and keen to sync on how things are going. I defo, as in definitely, could use some of your creative thinking to help with mine. Cheers, V. And so, what I'd like us to pay attention to. First of all, of course, you can see that I sent this email to myself, but that's just because I wanted to keep my friend's... actually, it's because I already replied to the email and then I wanted to resend it. And also I wanted to keep my friend, keep his privacy. But this is a real email. This is the exact text that I got literally a couple of days ago. And the title was a bit different, but I changed it to catch up. And so what is interesting about this? We're going to be looking at how we can apply natural language processing to this email in the next couple of tutorials, and it will help us work with a real life example. And then the other thing is that here you can see in Google, the Gmail app for iPhone, you can see that it's giving me some suggestions. Very interesting. It's saying, it's already giving me some quick replies that I can use. It can be, yes, I'm around, I'm back, or sorry, I'm not. Very interesting. So let's keep that in mind, and we will come back to this later. In the meantime, text of the email is here. What can we do with it? All right, so first things, we're going to start off simple. We're going to create a model. We're going to look at how we can create a model that will give us a yes/no response, because that's one of those questions. The question is, are you back in Australia? Let me know if you're around and keen to sync. So yes, no. Of course, it's better to have a long response, and that's the social norm, and it's the etiquette to like converse with people, not just say yes, no. But even let's try to get a yes/no response. Let's see how we would go about that, because that's the first step into NLP. And then further on, we will see how we can expand that even more. All right, so we're going to start off with a vector. A vector, or a just like an array, full of zeros. Let's call it a vector. It's easier like that. So just zeros, 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 zeros. How many zeros? Well, a lot of zeros. 20,000 elements in total. 20,000. Why is that? Well, it's because of the way that we're building this model. 20,000 is the number of words that are commonly used by the average native English language speakers. So here's a quick search on Google. How many words in the English? So that's the search I took. I came up with. How many words are there in the English language? 171,476 words. That's how many entries in the Oxford Dictionary, plus some obsolete words, plus derivative words, and so on. But also, you can see Google's giving us a suggestion that most adult native test takers range from 20 to 35,000 words. Average native test takers of age 8 already know 10,000 words. Average native test takers of 4 already know 5,000 words. And adult native test takers learn almost whatever. So I'm just going into so much detail. But the interesting thing here is that how many, like, what I wanted to point out, first of all, 20,000, and we will see why exactly we use this number, not more. What I wanted to point out is how many words are there in the English language. Even this in its own is actually, Google's applying natural language processing. It's looking at what we wrote, and then it's also checking other similar answers. How many words in the English language does the average person know? So that's not the question asked, but it came up with that. Then it came up with many other questions. So you can see that the irony is that even in this search on its own, we're already falling victim of natural language processing, even though that wasn't our intention. That's not what we're going to be talking about, but it's just funny that it came up. Anyway, so 20,000 words, and a fun fact is that we actually use about 3,000 words. Out of those 171,476 words, we only use 3,000 words, not just in conversational language, but you can see here, a vocabulary of just 3,000 words provides coverage for around 95% of common texts. 95% of common text that I'm assuming that's including books and stuff like that. So if you do the math, it's only use 1.75% of the total number of words in the English language. So as you can see, even that 3,000, like our 20,000 is more than even the 3,000 that covers 95% of the situation. So we're pretty good. We're definitely covered if we say that our vocabulary, all possible words that we can encounter, is going to fit into a vector of 20,000. So basically what we're saying, this is important, what we're saying is that every word in the English language has a position somewhere on this vector. So for example, the word if could have this position. So if we count 1, 2, 3, 4, 5, 6, the 7th position in our custom-made vector is the word if, and it's always going to be on that position. That's very crucial for this. For instance, the word badminton, let's just take, we can construct this vector any way we want. The word badminton could be on this position. It's always going to be on this position. And the word table is going to be on this position. And this is like how this bag of words model works. So just keep in mind that once we've taken out 20,000 words, and then we've assigned them a space, this space in this vector will be associated with. It'll be associated with the word if. This will be associated with the word badminton. This position will be associated with the word table. And the other thing is, here you can see I've grayed out the first two and the last one. First two are going to be reserved for SOS and EOS. SOS stands for start of sentence. EOS stands for end of sentence. And the last one will be reserved for special words. And that's for those words that you're wondering about. I can hear your brain churning right now. What about those other 150,000 words that we didn't take into account? What if they come up? Well, if they come up, we're going to just associate them with this last element. We can just throw them all in there. Any kind of words that we cannot recognize in the 20,000, we're going to throw them into that last element. All right, so let's go back to our email text. Here it is. Hello, Kirill. Checking if you're back in Oz. Let me know if you are around, etc., etc., etc. Cheers, V. And so let's see how this can be put into our bag of words. If you've probably noticed by now that this is our bag of words that we're constructing here. So now we're going to throw the text into this bag of words. How's that going to happen? I'm just going to throw it in, and then I'll explain how it happens. So there it is. That's the result. It of course depends on how we construct our vector, but this is our result in the way we construct our vector. And let's look at this way. So as we discussed previously, we took the 20,000 words and we associated each position with a word. And now we go through our text and then increase the counter in each position of the associated word. So hello, let's say in our vector it is in position number 5. Because we only have one hello in this whole email, we're going to put a 1 here. Kirill is definitely not an English language word, so we're going to have to put it into there. And the reason why there's 3 here is because we have Kirill, then Oz, and V. Those are not English language words, not among our 20,000. They're all going to go here. Then we've got the comma. Surprise, the comma also has a position. Let's say it was in position number 3, 6, 7, 8, 9. So the 9th position is associated with a comma because we have 1 comma in our email. Oh, actually we have 2 commas. Okay, so this should be a 2. But let's not think about that comma. Let's forget about that comma. I didn't notice it. So assuming we have 1 comma in our email, this is a 1. Checking, let's say that this element is associated with the word checking. This is a 1 because there's only one word, checking. If, it's a 2 because we have 2 ifs in our email. So it's going to be a 2. U is a 2 because we have 2 U's in our email, including the rest of the text. I don't think there's any more U's in there, and so on. So that's basically how we fill this bag of words. We just put in the quantity of words for every position. It's pretty straightforward. We're just filling in this vector. As you can see, it's going to be quite a sparse vector. There's going to be lots of zeros, almost 20,000 zeros, and some of the words are going to be filled in. Okay, and so what is our goal? So our goal, as we discussed before, is to come up with a reply yes or no to this email, which is now in the form of a vector. And how are we going to do that? Well, we're going to do it through training data. So we're going to look at all of the emails that I have replied to, because this is us training a model to reply to my emails, or in your case, in anybody's case, is going to be training a model to reply to their emails. We're going to look at training data. We're going to need some training data, and we're going to fish it out of the inbox or outbox. So let's look at a couple. So here we've got, hey mate, have you read about Hinton's capsule networks? And Kirill replied to that, no. So we're going to use that as a training example. The next one, did you like that recipe I sent you last week? The answer was yes. It was a good recipe, I guess. So here we go. So now we have 2, 3. Hi Kirill, are you coming to dinner tonight? Yes. Dear Kirill, would you like to service your car with us again? No. Are you coming to Australia in December? Yes. And so on. So ideally we would have tens or hundreds of thousands of emails like that and responses like that. Yes, no responses. Of course, it would be like a lot of groundwork to get that data, because we usually don't just respond yes, no to emails. So we'd have to look at this answer and understand what was the sentiment. The sentiment was no, or what was the overall, was it a yes or no, no, yes or no, and so on. Of course, this is kind of more of a theoretical example. Nobody's going to do this for their own inbox, but nevertheless, the point stands. So how would we use this training data? We would use a similar principle and convert each one of those emails to a vector. And again, each vector would be 20,000 elements long. So, I just threw some numbers in here to get the point across. It's not exactly accurate, but so we have these vectors, like lots and lots and lots of vectors, lots and lots and lots of responses, yes and no. And yeah, so now what we're going to do is we're going to apply a model. Once we have all this data, we're going to apply a model. So one of the models we can apply to create our bag of words, or one of the algorithms we can apply to create our bag of words model, is the logistic regression. So we apply the logistic regression to our yes/no responses, to this information that we have, and then once we have that model, once we've separated, so we know, we kind of like, we've modeled what goes into a yes, like what is likely to yield a yes, what is likely to yield a no, and the border between them. Then we can feed our actual email that we got into this model, and then get a response. So for instance, yes, and that's it. So we use all the training data to create a model. We feed in our actual email, which, this is important, which has exactly the same format. So you can see that every input here, every time we were training the data, the independent variable the independent variable vector always had the same length, 20,000. It always had the same format. So we know that this position always corresponds to a certain word. This position is always a certain word. This position, let's say 1, 2, 3, which word was it? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this was, this one was the if, right? So this corresponds to if, or something like that. So we know that it's the same format, it's always the same length, 20,000. So we can safely feed in this vector into there. It's got the same number of features. Bam, we get an answer. So for instance, we get yes. So, and then we can like look back, oh, what did the actual email say? It said, hello, Kirill, checking. Oh, okay. So based on my training, I would have most likely replied to this with a yes. Interesting. The other approach that we can take here, or first of all, let's put this on our diagram. There's our diagram, and that's a natural language processing algorithm, which is called bag of words. It sits over there. The other approach that we could apply here or take here is we could, instead of a logistic regression, we could use a neural network. We could, because we have a vector, right? So we have all these vectors, we could feed them into, as an input layer, like over 20,000 neurons, into our neural network. They would go through one hidden layer, two hidden layers, as many hidden layers as we want, our own decision on how to structure it, and then bam, we've got an output layer. It tells us yes or no. And so again, we'd use all this data that we have here, all our millions and millions and millions of emails and responses. We'd use that to train our neural network all through backpropagation and stochastic gradient descent. All the weights would be updated, and bam, we have an answer. So not bam, we have an answer. So we would use these answers here to train the network. We'd use the pairs, like the vector and the answer, vector answer. So to minimize the error, stochastic gradient descent, backpropagation, updated weights, bam, we have a neural network. It's all trained up. Now we feed in our vector here, which represents our new email, into the neural network, and voila, we get our answer. And in this case, might also be yes. They might yield different results, but if the models are constructed well, more or less, they should be coming up with similar or the same answers most of the time. And so in this case, we've got a deep natural language processing, or I didn't put the emphasis right there. We've got a deep natural language processing algorithm, right? Because we're using a neural network. And that is the difference. So in both cases, the bag of words model, in one case it's an NLP bag of words, in another case it's a deep NLP bag of words. But in both cases, it is still a bag of words. And it has its own limitations, and it has its own limitations and issues that are not that great. And so I'll point out one of them right now is that the response is very simple. It's just a yes or a no, right? Like we want something more sophisticated. We want like a conversation. We can't really have a conversation, can't really build a chatbot if you're just going to be saying yes, no all the time. So that's one of the limitations. We'll talk about some more of them in the upcoming tutorial, and we'll also see how to overcome those limitations and what models await us in the future. And I hope you enjoyed this tutorial. I really enjoyed going through all of this with you together, and I can't wait to see you next time. Until then, enjoy natural language processing.